Hello there, and welcome to the Sleepy Science Channel. Tonight, we'll be exploring some of the strangest ideas in physics that reveal how bizarre our universe really is. Physics can often feel like a boring subject of formulas and classrooms, but it is really a way of observing the true magic of reality. It explains why time is not as steady as it feels, why matter is far less solid than it appears, and why forces we cannot see can shape everything we touch. Some facts will feel familiar at first, then open into something much stranger. Others may sound almost impossible, even though they belong to the real world. Along the way, we will move from everyday objects to distant space, from simple motion to the hidden rules beneath atoms. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is settle in. Let your shoulders relax and notice your eyes grow heavy. And as the day begins to gently fade away, join me as we explore this fascinating side of reality together. Let's begin. Empty space is not truly empty at all. A perfect vacuum sounds like the ultimate nothing, but physics says it still has activity. Remove every atom from a sealed chamber and something remains. Fields still fill the region. These fields can twitch in tiny ways because the quantum world never sits perfectly still. For a brief moment, energy can appear in a form that almost looks like particles, arriving and vanishing before ordinary matter can catch them. Scientists do not treat this as fantasy. This restless vacuum helps explain real effects measured in laboratories, including a tiny force between metal plates placed extremely close together. It also changes how atoms behave with remarkable precision. The strange part is that nothingness is not just an empty stage where physics happens. It has properties of its own. Even when every visible thing is gone, reality still has a kind of hidden texture. The universe is not built on silence. It is built on fields that never completely stop moving. Time actually runs slower near massive objects. A clock beside Earth's surface ticks a little more slowly than a clock high above it. The difference is tiny, but it is real. This happens because mass changes the shape of time itself. Near a heavy object, time does not pass at quite the same pace as it does farther away. The effect becomes more extreme near things with enormous gravity. Close to a black hole, minutes for one person could correspond to far longer for someone watching from a safer distance. This is not just a clever idea from science fiction. It has been measured with incredibly accurate clocks. Raise one atomic clock above another, and the higher clock gains a tiny amount of time. That means time is not a universal rhythm beating the same way everywhere. It is part of the physical world, and it responds to gravity. Every second you experience is local to where you are in the universe. Light can behave like both a wave and a particle. Shine light through two narrow openings, and it can make a pattern like ripples crossing on water. Send the same light into certain detectors and it arrives in separate packets. That is the puzzle. Light does not fit neatly into the everyday categories our senses prefer. Sometimes it spreads, overlaps, and interferes like a wave. Sometimes it strikes a surface as if it came in individual pieces. These pieces are called photons, and each one carries a precise amount of energy. The famous double-slit experiment shows the weirdness most clearly. Even when photons are sent one at a time, the final pattern still builds up like something has explored more than one path. Physics does not say light is secretly one familiar thing wearing a disguise. It says the familiar categories are too small. Light reveals a deeper rule of nature, where possibility itself has structure before an event becomes definite. Most of your body is empty space. Your hand feels solid because atoms push back against other atoms. Yet inside each atom, the central nucleus is incredibly tiny compared with the surrounding region occupied by electrons. If an atom were enlarged to the size of a stadium, its nucleus would be like a small object near the center, while the electron region would stretch far outward. That means the matter in your body is not packed like bricks. It is more like organized charge and motion, held together by forces. You cannot pass through a wall because the electrons in your atoms repel the electrons in the wall. Solidity is not caused by everything being filled in. It comes from interactions that are strong enough to stop ordinary objects from sliding through each other. This makes everyday life feel stranger. A table, a stone, and your own bones seem dense and continuous, but matter is mostly structured emptiness with powerful rules. A teaspoon of neutron star would weigh billions of tons. After a massive star collapses, its core can become so compressed that protons and electrons are forced together. The result is matter dominated by neutrons, packed beyond anything found on Earth. In a neutron star, a mass greater than the Sun can fit inside a sphere only about the size of a city. That level of density is almost impossible to picture. A small spoonful would weigh more than mountains. Its gravity would be so intense that ordinary material could not support it here. Neutron stars are not just heavy objects. They are laboratories made by the universe, where matter is pushed to the edge of what physics can describe. Some spin with extraordinary speed and sweep beams of radiation through space. Others collide and help create heavy elements. A neutron star shows what happens when gravity crushes matter past every familiar limit and leaves behind something nearly beyond imagination. The universe has a speed limit built into reality. Nothing carrying mass can outrun light in a vacuum. This is not because engines are too weak or technology has not advanced enough. It is because speed changes the relationship between energy, time, and motion. As an object with mass moves faster, adding more energy gives less and less extra speed. To reach light speed would require an infinite amount of energy, which makes the target unreachable for ordinary matter. Light itself travels at that limit because photons have no rest mass. This rule links distant galaxies to the smallest particles in a laboratory. It also protects cause and effect. If information could move faster than light, events could be seen in impossible orders, and the logic of reality would start to break. The speed of light is not just a fast number. It is a boundary woven into the structure of space and time. Particles can affect each other across huge distances instantly. When two quantum particles become entangled, their properties are described by one shared state. Separate them by a room, a continent, or far more, and a measurement of one is still connected to the other. This troubled Einstein because it seemed to challenge the ordinary idea that distant objects need time to influence each other. Experiments have shown that entanglement is real, and the results are stronger than any hidden local instruction could explain. Still, it cannot be used to send a message faster than light. That detail matters. The link is not a secret radio signal racing through space. It is a sign that quantum objects do not always possess definite separate properties before measurement. Entanglement is now used in serious technology research, including quantum computing and secure communication. It suggests that nature is less divided into independent pieces than everyday experience makes it seem. Gravity is the weakest force, yet it shapes galaxies. A fridge magnet can lift a paperclip against the pull of the entire Earth. That simple moment shows how weak gravity is compared with electromagnetism. The reason gravity dominates the largest scales is different. It always attracts ordinary matter, and it reaches across unlimited distance. electric charges usually balance out because positive and negative charges cancel each other. Gravity does not cancel that way. Every star, planet, cloud, and grain of dust adds to the pull. Across vast stretches of space, those tiny pulls collect into enormous structures. Gravity gathers gas into stars, holds moons in orbit, and guides galaxies into clusters. It is weak in a handheld experiment, but relentless on cosmic scales. This makes it one of the great surprises of physics. The gentlest force in daily life becomes the architect of the universe when enough matter is involved and enough time passes. Black holes can stretch light until it disappears. Light escaping from strong gravity loses energy as it climbs away. Near a black hole, this effect becomes extreme. A beam that begins as visible light can be stretched into longer wavelengths until it fades beyond what human eyes could see. At the event horizon, escape becomes impossible. That boundary is not a physical surface like a shell. It is the point where every future path leads inward. To a distant observer, light from falling material appears increasingly red and dim. This is one reason black holes are detected through the behavior of matter around them, rather than by direct glowing surfaces. Gas spiraling nearby can become incredibly hot and bright before crossing the point of no return. The darkness is not emptiness in the usual sense. It is a region where gravity has bent the possible paths of light so severely that the universe cannot send a signal back out. The atoms in your body were forged inside stars. The hydrogen in you is ancient, but many heavier atoms needed stars to exist. Carbon, oxygen, calcium, and iron did not simply appear in finished form at the beginning of the universe. They were built through nuclear reactions inside stars and through violent stellar deaths. When massive stars explode, they scatter newly made elements into space. Later, that enriched material can become part of new stars, planets, oceans, and living bodies. This means your bloodstream carries iron that was once formed in a cosmic furnace. The calcium in your bones has a history older than Earth. The oxygen you breathe belongs to a chain of events that began long before life existed here. Physics turns the human body into evidence of cosmic recycling. You are not separate from the history of stars. You are made from material that traveled through generations of them before becoming part of you. A falling object feels weightless before it hits anything. Step off a platform in a safe training drop, and during the fall, your body no longer pushes against the ground. That missing push is what you usually feel as weight. Gravity is still acting, but every part of you is accelerating together. Because there is no floor pressing upward, you experience weightlessness. This is the same principle behind astronauts floating in orbit. They have not escaped gravity. They are falling continuously around Earth, moving forward fast enough that the ground curves away beneath them. The feeling is not caused by being far from a planet. It comes from being in free fall. Even a dropped elevator would create weightlessness inside for a brief and dangerous moment. This changes the ordinary meaning of weight. It is not simply gravity pulling downward. It is the force you feel when something prevents you from falling freely along with everything around you. Sound cannot travel through empty space. Sound is not a thing that moves by itself. It is a vibration passed from particle to particle through matter. In air, molecules bump into their neighbors and carry pressure waves outward. In water, the wave travels through tightly packed molecules. In metal, it can move even faster because atoms are strongly connected. Take away the material, and there is nothing to carry the disturbance. That is why explosions in space would not roar across a vacuum the way films often suggest. A spacecraft could shake from an impact if the vibration reached its structure, but sound would not cross the empty gap as air pressure. This makes space stranger than it looks on screen. It can contain intense radiation, violent collisions, and enormous energy. Yet a person outside without a medium would hear none of it. Sound needs a physical messenger, and a vacuum refuses to provide one. The sun bends starlight passing near its edge. During a solar eclipse, the sun is hidden enough for nearby stars to be seen. In 1919, observers measured stars appearing slightly out of place because their light had passed close to the sun. The results supported Einstein's idea that gravity bends space-time and light follows the curved path. The sun was not pulling on light as if it were a thrown ball. Instead, its mass changed the geometry through which the light traveled. This effect is called gravitational lensing, and it has become a powerful tool in astronomy. Massive galaxies can bend and magnify the light of objects behind them, letting telescopes glimpse things that would otherwise be too faint or distant. Sometimes the bending creates arcs or multiple images of the same background source. Gravity can act like a lens without glass. A star can reveal the shape of space by shifting the light that passes beside it. Hot water can sometimes freeze faster than cold water. This surprising effect is known as the Mpemba effect, and it has puzzled scientists for decades. It does not happen every time, which makes it even more intriguing. Under certain conditions, warmer water can reach ice before cooler water placed in the same freezer. Several processes may be involved. Hot water can evaporate more, leaving less liquid behind. It can also create different convection currents, which move heat around inside the container. Dissolved gases may change too, and the contact between the container and the freezer surface can matter. The key lesson is that temperature alone does not tell the whole story. Freezing depends on how heat leaves the water, how the water moves, and what changes while it cools. A simple ice tray can become a messy physics experiment. The weirdness is not that hot always beats cold. It is that a familiar process can hide several competing mechanisms. Your GPS works because Einstein was right. Satellites carry clocks that must stay synchronized with clocks on Earth. Without precise timing, a navigation device could not calculate location accurately. The problem is that satellite clocks do not tick at exactly the same rate as clocks on the ground. Their motion affects time, and their height above Earth affects it too. One effect makes the satellite clocks run a little slower. The other makes them run faster. Engineers correct for both, using ideas from special and general relativity. If those corrections were ignored, location errors would grow quickly, and the system would become useless for everyday navigation. This means a phone giving directions relies on physics that once sounded almost unbelievable. Einstein's theories are not sealed away in textbooks. They are built into modern timing networks. Each mapped route depends on the fact that time changes with speed and gravity, even when the differences are extremely small. A spinning figure skater demonstrates conservation of angular momentum. When a skater pulls their arms inward, their spin rate increases. No engine suddenly turns on. No hidden push appears. The change comes from a rule of rotating motion. With less mass spread far from the center, the skater must spin faster to keep the same angular momentum. Stretch the arms outward again, and the rotation slows. The same principle helps explain many spinning systems. A collapsing cloud of gas can rotate faster as it shrinks. A diver can tuck during a flip to speed the rotation, then open out to slow before entering the water. This rule is beautiful because it can be felt in the body and seen across space. It connects a rink performance with the motion of planets forming around young stars. Physics often hides in ordinary movement. A graceful spin on ice becomes a visible demonstration of one of nature's strict accounting rules. A rainbow forms because different colors bend by different amounts. Sunlight looks white, but it contains many colors mixed together. When sunlight enters a raindrop, it slows and bends. Inside the drop, it reflects from the back surface and bends again as it leaves. Each color changes direction by a slightly different amount, so the mixed light spreads into a band. Red appears toward the outside of the arc, while violet appears toward the inside. The rainbow is not sitting at a fixed place in the sky like an object. It depends on the position of your eyes, the sun, and the falling rain. Someone standing beside you sees their own rainbow from a slightly different set of droplets. That makes the sight more personal than it seems. A rainbow is a geometry event made of sunlight and water. It is familiar enough for a child to name, yet precise enough for physics to explain angle by angle. Lightning is hotter than the surface of the sun. A lightning bolt heats the air around it to an extreme temperature in a fraction of a second. The air expands explosively, and that sudden expansion creates thunder. The flash is not just a bright spark. It is a powerful electrical discharge finding a path through the atmosphere. The channel can reach temperatures several times hotter than the sun's visible surface, though only for a brief moment. That heat tears molecules apart and allows air to conduct electricity. The path often branches because the electric field searches through uneven pockets of air. Before the main flash, faint leaders step downward from the cloud, while upward connections rise from the ground. When one connection completes the path, the brilliant return stroke follows. Lightning looks instant from a distance, but it is a rapid sequence of physical steps. A storm cloud becomes a huge electrical machine, and the sky becomes its circuit. Glass is a solid that still behaves strangely under stress. Glass feels hard, but its inner structure is not arranged like a regular crystal. In a crystal, atoms repeat in an orderly pattern. In glass, the atoms are locked into a disordered arrangement, more like a liquid whose motion has become frozen. That does not mean old windows flow downward over centuries in any ordinary way. That common story is misleading. The uneven thickness in antique glass usually comes from old manufacturing methods. The real strangeness is different. Glass can withstand pressure in some situations, yet a tiny crack can concentrate stress so strongly that the whole piece fails suddenly. That is why a small scratch can matter. Tempered glass uses controlled stress inside the material to change how it breaks. A simple pane is not as simple as it looks. Its strength depends on hidden structure, surface flaws, and the way force travels through a disordered solid. Magnets work because countless electrons act like tiny spinning charges. A magnet is not powered by a secret battery inside the metal. Its strength comes from the behavior of electrons. Electrons have a quantum property called spin, which makes them act like tiny magnetic sources. In many materials, these magnetic effects point in random directions and cancel out. In a strong magnet, many of them line up in the same direction, across regions called domains. When enough domains align, the whole object gains a north and south pole. That is why cutting a magnet in half does not produce a lonely north pole and a lonely south pole. Each piece becomes a smaller magnet with both poles. Heat can weaken a magnet because disorder breaks up the alignment. A hard knock can also disturb it. The familiar pull on a fridge door comes from countless quantum scale alignments working together. Magnetism feels simple in the hand, but its origin is deeply atomic. Superconductors can carry electricity with no resistance at all. In an ordinary wire, moving electrons lose energy as heat because they keep interacting with the material around them. That is why cables warm up and power lines waste some of the electricity they carry. In a superconductor, the rules change. Cool certain materials enough, and electrical resistance drops to exactly nothing. A current can keep flowing in a closed superconducting loop for years without needing a battery to push it along. The effect happens because electrons stop behaving like separate travelers fighting through a crowd. They form linked pairs that move together through the material in a coordinated quantum state. Superconductors also push magnetic fields out of their interior, which leads to some of their most dramatic demonstrations. A small magnet can hover above them with eerie stability. The dream is to find superconductors that work easily at everyday temperatures. If that happens, power grids, medical scanners, and transport systems could change in a very direct way. A levitating train can ride on invisible magnetic forces. A maglev train does not need steel wheels gripping rails in the usual way. Instead, powerful magnetic systems lift and guide it above the track. Once the train is hovering, there is far less contact friction to fight, so the ride can become smoother and faster. Some designs use attraction, pulling the vehicle upward toward magnets in the guideway. Others use repulsion, pushing it away from the track with carefully controlled fields. The result looks almost unreal because there is no obvious support underneath. The train is being held in place by forces you cannot see, but can measure with precision. This is physics turned into transport. The same basic idea that makes two magnets push apart can help carry hundreds of passengers at high speed. It also shows that levitation does not have to mean magic. Under the right engineering, a moving machine can float on mathematics, electricity, and magnetism. Quantum particles can tunnel through barriers they should not cross. In the everyday world, a ball that lacks enough energy to climb a hill simply rolls back. A quantum particle does not always follow that familiar rule. When it meets a barrier, its wave-like description can extend slightly through the other side. Sometimes the particle is later found beyond the barrier, even though ordinary thinking says it never had enough energy to pass. This is called tunneling, and it is not a rare curiosity hidden in equations. It helps the sun shine because particles inside stars can get close enough to fuse more often than classical physics would allow. It also makes certain electronic devices work, including scanning tunneling microscopes that can image surfaces atom by atom. Radioactive decay can involve tunneling too, as particles escape from atomic nuclei. The astonishing part is that nature sometimes treats a barrier less like a wall and more like a probability that can be crossed. Water expands as it freezes, unlike most substances. Most materials shrink when they cool because their molecules settle closer together. Water breaks that pattern in a way that changes the planet. As it freezes, its molecules arrange themselves into an open crystal structure. That structure takes up more room than the same molecules did as liquid water. This is why a sealed bottle can burst in a freezer, and why cracks in rock can widen during winter. Water seeps into a small gap, freezes, expands, and pushes the sides apart with surprising force. Over many cycles, this helps break stone into soil and shape landscapes. The same property also affects lakes, rivers, and living things. It means frozen water behaves like a bulky version of its liquid self, rather than a tightly packed one. Something as ordinary as ice in a drink is showing a deep molecular oddity. Water is familiar, but it is not normal. Ice floats because its crystal structure makes it less dense. If frozen water sank, winter would be far more dangerous for life in lakes and ponds. Ice stays on top because its open crystal structure makes it less dense than liquid water. That floating layer becomes an insulating cover. Beneath it, water can remain liquid, giving fish and other organisms a place to survive until warmer conditions return. This simple detail matters on a planetary scale. It helps protect freshwater ecosystems and affects how heat moves between oceans and the atmosphere. The physics begins with the shape of the water molecule and the way neighboring molecules connect as freezing begins. Those connections create a rigid pattern with more space inside it. The result is visible every time ice cubes bob at the surface of a glass. A small floating cube is not just a kitchen detail. It is evidence of a molecular arrangement that helps keep parts of the living world from freezing solid. A vacuum can make water boil at room temperature. Boiling is not only about making water hot. It happens when the pressure of water vapor can push back against the surrounding pressure. At sea level, that usually requires high heat because the air above the water presses down strongly. Lower the outside pressure enough, and the water can boil without becoming hot in the normal sense. In a vacuum chamber, room temperature water can bubble as if it were on a stove. The strange part is that boiling can then cool the remaining water, because the most energetic molecules escape first. This is why pressure matters so much in cooking, weather, and space survival. On a high mountain, water boils at a lower temperature than it does near the coast. In the near vacuum of space, exposed liquids behave in ways that feel deeply unnatural. Boiling is not simply heat winning. It is a contest between vapor and the pressure around it. Astronauts orbit Earth by constantly falling around it. A spacecraft in orbit is not floating because gravity has vanished. Earth's gravity still reaches it strongly. The trick is sideways speed. Imagine throwing a ball so fast that as it falls, the planet curves away beneath it. It never reaches the ground because its path keeps missing Earth. That is orbit. Astronauts inside share the same falling motion as their spacecraft, so nothing presses them against the floor. They drift because everything around them is falling together. This is why the phrase zero gravity can be misleading. The better idea is continuous freefall. The International Space Station circles Earth while constantly dropping toward it, yet its forward motion keeps it from crashing down. This turns falling into a stable path through space. It is one of the most elegant ideas in physics. With enough speed, a fall does not end at the ground. It becomes a journey around the world. A feather and hammer fall together on the moon. On Earth, a feather drifts slowly because air resistance pushes against it. A hammer cuts through air far more easily, so it lands first. Remove the air, and that familiar difference disappears. During an Apollo mission, an astronaut dropped a feather and a hammer on the moon, and they struck the ground together. The demonstration showed a rule that Galileo had argued centuries earlier. Gravity gives falling objects the same acceleration when no other force gets in the way. Mass changes how hard an object is to move, but gravity pulls more strongly on greater mass in exactly the same proportion. Those effects balance. The moon made the lesson visible because there is no thick atmosphere to complicate the fall. It is a beautiful example of physics stripping away distraction. Two objects that seem completely different obey the same simple rule when the universe is allowed to show it cleanly. The moon is drifting away from Earth every year. The moon looks like a permanent companion, but its distance is slowly changing. Laser measurements show that it moves farther away by a few centimeters each year. The cause is tied to tides. The moon pulls on Earth's oceans, and Earth's rotation carries those tidal bulges slightly ahead of the moon's position. That offset gives the moon a tiny forward gravitational tug. Over time, it gains orbital energy and moves outward. Earth pays the price by spinning a little more slowly, which makes days gradually lengthen across deep time. This exchange has been happening for ages. Ancient Earth had shorter days, and the moon appeared larger in the sky. The effect is slow enough to be invisible in a human lifetime without instruments, yet steady enough to reshape the history of the Earth-Moon system. Even the calm face of the moon belongs to a changing relationship. Tides happen because gravity pulls unevenly across Earth. The moon's gravity does not pull every part of Earth with the same strength. The side facing the moon feels a slightly stronger pull than Earth's center. The far side feels a slightly weaker pull. This difference stretches the oceans into tidal bulges. As Earth rotates through those bulges, coastlines experience rising and falling water. The sun also contributes, which is why tides become especially strong when the sun, Earth, and moon line up. The interesting part is that tides are not simply water being lifted straight upward beneath the moon. They are the result of gravity changing across distance. The same principle can stretch moons, heat interiors, and even tear objects apart if they pass too close to something massive. On Earth, the effect arrives as a predictable rhythm at the shore. Behind that rhythm is a lesson about gravity. It does not only pull, it can stretch. A day on Venus lasts longer than its year. Venus takes less time to orbit the Sun than it takes to rotate once on its axis. That means a Venusian year is shorter than a Venusian day, at least by the way scientists measure rotation. The planet also spins backward compared with most planets, so the sun would rise in the west and set in the east if you could stand safely on its surface. Venus is almost the same size as Earth, but its rotation is shockingly different. Scientists think past gravitational interactions, atmospheric effects, and ancient impacts may all have played a role. The thick atmosphere adds another layer of strangeness, because fierce high-altitude winds circle the planet much faster than the solid surface turns. Venus shows that a planet does not have to behave like a familiar clockwork ball. Two neighboring worlds can form in the same solar system and end up with completely different rhythms. Saturn would float if you found a big enough ocean. Saturn is enormous, yet its average density is lower than water. That does not mean it has a solid surface that would bob like a beach ball. It is a giant planet, made mostly of hydrogen and helium, with layers that become stranger and more compressed deeper inside. Still, the density comparison is real and wonderfully surprising. Spread Saturn's mass across its huge volume, and it comes out lighter than an equal volume of water. This happens because the planet is mostly light gases, and it is puffed out to a vast size. Saturn's rings make it look delicate, but its atmosphere hides immense pressures below the cloud tops. Descend far enough and the gases become dense fluids, then exotic forms of matter. The floating idea is impossible as a practical experiment, but it captures a startling truth. One of the most majestic planets in the sky is, on average, astonishingly light. Jupiter protects Earth by attracting many wandering space rocks. The largest planet in our solar system has enormous gravity, and that gravity changes the paths of comets and asteroids. Sometimes Jupiter pulls dangerous objects away from the inner solar system. Sometimes it captures them, breaks them apart, or sends them into new orbits. In 1994, fragments of comet Shoemaker-Levy 9 slammed into Jupiter, leaving huge dark scars in its atmosphere. That event showed how dramatically the giant planet can intercept wandering material. The story is not perfectly simple because Jupiter can also redirect objects inward under some conditions. Still, its influence on the solar system is massive. It acts like a gravitational gatekeeper, constantly altering the traffic of smaller bodies. Earth does not move through space alone. It shares a system shaped by the biggest planet's pull. Jupiter reminds us that survival here may depend partly on events happening far beyond our own sky. The sun loses mass every second by shining. Sunlight is not free. It carries energy away from the sun, and energy has mass. Deep in the solar core, nuclear fusion turns hydrogen into helium. A small amount of mass becomes energy during that process, and the energy eventually escapes as light and other radiation. Because of this, the sun becomes lighter every moment. The amount is enormous by human standards, yet tiny compared with the sun's total mass. It can shine for billions of years because it began with such a vast supply of hydrogen. This is one of the most direct examples of mass and energy being connected. Every patch of sunlight on your skin is part of the sun's slow transformation. The star is spending itself to keep glowing. It is not burning like wood in a fireplace. It is changing matter into energy in its core, then releasing that energy across the solar system. Sunlight takes several minutes to reach your skin. When you step outside on a bright day, the light touching you has already crossed space from the sun. That journey takes a little over 8 minutes. The photons that finally reach Earth travel through the vacuum at light speed, but their earlier history inside the sun can be much longer. Energy created in the core does not simply fly straight out. It can be absorbed and re-emitted many times as it works through the dense inner layers. By the time sunlight leaves the visible surface, it is ready for the quick trip across the space between worlds. This gives daylight a hidden time story. The warmth on your face began as nuclear energy deep inside a star, escaped through a crowded interior, then raced across millions of kilometers to arrive here. Sunlight feels immediate, but it is never truly instant. Every beam is a message from the recent past. Some stars are so dense that atoms collapse inward. In ordinary matter, atoms keep their structure because electrons occupy space around nuclei. In the crushed remains of certain massive stars, gravity becomes strong enough to overwhelm that arrangement. Electrons and protons are forced together, creating neutrons and releasing ghostly particles called neutrinos. The star's core becomes packed with matter in a form unlike anything on Earth. This collapse can happen during a supernova, when the outer layers blast into space while the core is squeezed into an extreme remnant. The result may be a neutron star, where normal atomic structure no longer survives. This is not just a smaller version of familiar matter. It is a different state produced by gravity at terrifying intensity. The existence of such stars shows that atoms are not indestructible little building blocks under all conditions. Put enough mass in one place, and even the architecture of matter can be forced to give way. A pulsar can spin hundreds of times each second. A pulsar is a rapidly rotating neutron star that sends beams of radiation into space. If one of those beams sweeps across Earth, radio telescopes detect regular pulses, almost like a cosmic lighthouse. The timing can be astonishingly precise. Some pulsars rotate many times in a single second, and millisecond pulsars spin even faster. Their speed comes from the collapse of a rotating star. As the core shrinks dramatically, it spins faster for the same reason a skater speeds up when pulling in their arms. Pulsars also have powerful magnetic fields that guide radiation from their poles. At first, their steady signals seemed so strange that scientists briefly wondered whether they might be artificial. They were not messages. They were nature turning a dead star into an extraordinary clock. A pulsar proves that the universe can produce timing more accurate than many human-made devices, using an object only about city-sized. Neutrinos pass through your body by the trillions each second. These particles are produced by the sun, exploding stars, nuclear reactions, and other high-energy events. They are incredibly hard to stop because they barely interact with ordinary matter. Most pass through Earth as if the entire planet were almost transparent. Right now, huge numbers of solar neutrinos are crossing your body without leaving a trace. To detect them, scientists build enormous instruments deep underground or under ice, where rare interactions can be separated from background noise. A neutrino can travel through a light year of lead with a good chance of getting through. That sounds impossible, but it reflects how weakly these particles respond to the forces that shape familiar matter. They carry information from places light cannot easily escape, including the hearts of stars. Neutrinos are like nearly silent messengers from violent processes. They remind us that the universe is passing through us constantly, whether we notice it or not. Dark matter outweighs normal matter across the universe. Stars, planets, gas, dust, and people are made of ordinary matter. Yet when astronomers study galaxies, they find that visible material cannot explain the motions they observe. Stars orbit too quickly in the outer regions of galaxies. Galaxy clusters hold together more strongly than their visible mass should allow. Light from distant objects is bent more than expected by matter we can see. These clues point to something invisible that has gravity but does not shine, absorb, or reflect light in the usual way. Scientists call it dark matter. It is not dark because it is black. It is dark because it does not interact with light enough for telescopes to see directly. The evidence appears across many scales, which makes the mystery hard to ignore. Most matter in the cosmos may be of a kind that passes through ordinary matter almost unnoticed, shaping galaxies from behind the scenes. Dark energy appears to push the universe apart faster. In the late 1990s, astronomers studying distant exploding stars found something unexpected. The expansion of the universe was not slowing under gravity, as many had assumed. It was speeding up. The name given to the unknown cause is dark energy. This does not mean scientists understand exactly what it is. It is a label for whatever drives the accelerated expansion. One possibility is that empty space itself has an energy that does not dilute as the universe grows. If so, more space means more of this effect, and distant galaxies are carried away from each other ever faster. Dark energy is not a force you can feel in a room. It shows up across the largest distances, where the history of cosmic expansion can be measured. The mystery is enormous. The universe is not just expanding after an ancient beginning. Something appears to be affecting the pace of that expansion today. The observable universe is not the whole universe. There is a limit to how far we can see, not because telescopes are too weak, but because light has had only a finite time to travel since the early universe became transparent. The observable universe is the region from which light has had time to reach us. Beyond that boundary, there may be far more universe that is simply outside our current view. It might contain galaxies, stars, and physical conditions much like those we can observe. It could also be larger than we can comfortably imagine. The edge of the observable universe is not a wall in space. It is a horizon set by time, light, and cosmic expansion. Observers in a distant galaxy would have their own observable region centered on them. This changes the meaning of the word universe in everyday speech. What we can study may be only the visible portion of a far larger reality. Cosmic background radiation is leftover heat from the early universe. Look far enough in every direction with microwave-sensitive instruments, and space glows with a faint afterglow. This radiation comes from a time when the universe cooled enough for light to travel freely through space. Before that, the cosmos was a hot, dense plasma that scattered light constantly. When atoms finally formed, light was released and began stretching with the expansion of the universe. Today, it arrives as cold microwave radiation from all directions. It is not coming from stars or galaxies. It is a relic of the young universe itself. Tiny variations in its temperature reveal the seeds of later cosmic structure. Regions that were slightly denser eventually helped form galaxies and clusters. This background glow is one of the strongest pieces of evidence for the universe's hot beginning. It turns the sky into an ancient record. With the right instruments, we can still detect heat from the universe's childhood. The first atoms formed long before the first stars. For a long, early period, the universe was too hot for atoms to hold together. Electrons could not settle around nuclei because energetic light kept knocking them loose. As the universe expanded, it cooled. Eventually, electrons joined with nuclei to form mostly hydrogen and helium atoms. This happened before stars existed, which means the cosmos had a dark age. There was matter, gravity, and radiation, but no starlight yet filling the darkness. Over time, slightly denser regions pulled in more gas. Those growing clouds eventually collapsed enough to ignite the first stars. The formation of atoms was a crucial turning point because it allowed light to travel freely and matter to gather in new ways. It was not a dramatic flash like a star exploding. It was a cooling threshold that changed what the universe could become. Before the first star shone, atoms had to make the darkness possible. Every element heavier than helium needed violent cosmic events. The early universe made mostly hydrogen and helium with only tiny traces of a few light elements. The rest of the periodic table needed later cosmic processes. Stars fuse light elements into heavier ones during their lives. Massive stars build elements in layers as their cores become hotter and denser. Some elements are released when stars shed material. Others require explosive deaths, where extreme temperatures and pressures drive rapid nuclear reactions. The heaviest elements often need even more dramatic events, such as neutron-star collisions. This means the periodic table is not just a classroom chart. It is a record of astrophysical history. Oxygen, silicon, iron, silver, iodine, and uranium each carry clues about where and how they were made. The universe began chemically simple, then became rich through fire, collapse, and collision. Every complex material on Earth exists because the cosmos learned to make heavier atoms over time. Gold may come from colliding neutron stars. For a long time, scientists knew that heavy elements needed extreme conditions, but the exact cosmic source of much gold remained uncertain. Then, astronomers observed a neutron star merger. The event produced gravitational waves and a burst of light that showed signs of heavy element creation. In such collisions, neutron-rich matter is thrown into space. Atomic nuclei rapidly capture neutrons, then decay into heavy elements, including gold and platinum. This process can create amounts of precious metal far beyond anything found on Earth. The gold in a ring or circuit board may have begun in one of the most violent events in the universe. It was later mixed into interstellar material, folded into a forming solar system, and trapped inside Earth. The value of gold feels human, but its origin is cosmic. It is not just rare in the ground. It may be the cooled remnant of two dead stars crashing together. A black hole is not a cosmic vacuum cleaner. A black hole does not suck in everything around it, simply because it exists. From far away, its gravity behaves like the gravity of any object with the same mass. If the Sun could somehow become a black hole without changing mass, Earth would not be pulled straight inward. It would keep orbiting because the gravitational pull at our distance would be essentially the same. What makes a black hole extreme is how much mass is packed inside a very small region. Get too close, and there is no safe path back out. Stay far enough away, and ordinary orbital physics still matters. This helps remove one of the biggest misconceptions in space science. Black holes are dangerous near their boundaries, not magical mouths roaming the universe. They can feed on nearby gas and stars under the right conditions, but they do not automatically consume galaxies. Their power comes from compactness, not endless reach. Falling into a black hole would make time look strange. To someone falling inward, the trip could feel finite and terrifyingly direct. To a distant observer, the view is very different. Light from the falling object would take longer and longer to escape as it neared the event horizon. The object would appear to slow, dim, and redden, never quite seeming to cross the boundary in ordinary view. This does not mean the traveler safely freezes in place from their own perspective. It means different observers slice time in different ways around extreme gravity. Near the black hole, the distortion becomes so strong that everyday intuition fails. Signals sent outward become harder to receive. The final moments become increasingly hidden from the outside universe. This is one reason black holes feel so unsettling. They do not merely trap matter. They warp the relationship between events and observation. A fall into one is also a journey into the limits of how time can be compared. Black holes can slowly lose energy through radiation. Classically, nothing escapes from inside a black hole's event horizon. Quantum theory adds a strange twist. Stephen Hawking showed that black holes should emit a faint form of radiation because of effects near the horizon. This radiation carries energy away, so a black hole can gradually lose mass. For large black holes, the process is incredibly slow, and the radiation is extremely cold. A stellar mass black hole would take far longer than the current age of the universe to evaporate. Tiny, hypothetical black holes would radiate much more strongly. The idea links gravity, quantum physics, and thermodynamics in one of the deepest puzzles in science. It also suggests black holes have temperatures and entropy, which makes them less like simple holes and more like physical systems with hidden information. Hawking radiation has not turned black holes into visible lamps. Its power is conceptual. It shows that even darkness may not be completely final. The Milky Way contains a giant black hole at its center. At the heart of our galaxy sits Sagittarius A star, a compact object with the mass of millions of suns. Astronomers confirmed its nature by tracking stars that orbit incredibly close to the galactic center. Those stars move around an unseen object so massive and compact that a supermassive black hole is the best explanation. One star completes a tight orbit that allowed scientists to map the central gravity with remarkable precision. The black hole is currently not feeding as violently as those in some active galaxies, which is fortunate for our view from Earth. Around it, gas, dust, and stars move through a crowded region shaped by immense gravity. This discovery changes the way we imagine the Milky Way. Our galaxy is not just a broad band of stars across the night sky. It has a dark central anchor, and millions of stellar paths are influenced by the mass hidden there. Our galaxy is moving through space at astonishing speed. The Milky Way is not standing still in a cosmic background. It rotates, moves within the local group of galaxies, and travels along with larger cosmic flows. Our Sun orbits the galactic center at a tremendous speed, taking hundreds of millions of years to complete one circuit. The galaxy itself is also moving relative to the afterglow of the early universe. This motion can be detected because that background radiation looks slightly warmer in one direction and slightly cooler in the opposite direction. It is like feeling a cosmic headwind through temperature. On top of that, the Milky Way and Andromeda are moving toward each other under gravity. Space may look calm on human timescales, but everything is in motion. The ground feels steady because we share Earth's movement. In reality, we are riding a planet around a star inside a galaxy, through a universe where stillness is almost never the default. Galaxies can collide without most stars actually touching. When two galaxies meet, the event sounds like a universe-sized crash. In reality, the stars inside them are separated by such vast distances that direct collisions between stars are extremely unlikely. The real drama happens through gravity. Each galaxy pulls on the other, stretching long streams of stars and stirring huge clouds of gas. Those gas clouds can slam together, compress, and trigger bursts of new star formation. A galactic collision can therefore create new stars even while most existing stars pass through the encounter untouched. Our own Milky Way is expected to merge with the Andromeda Galaxy in the far future. The night sky would change completely over immense time as the two great systems bend into new shapes. This is cosmic violence, without the kind of impact we imagine from everyday life. Galaxies do not need to smash star against star to transform each other. Gravity alone can remake their structure. The universe is expanding faster than light in distant regions. The speed limit of light applies to things moving through space, but space itself can expand. That distinction is crucial. Very distant galaxies can recede from us faster than light because the space between us and them is stretching. They are not locally racing through their own neighborhoods faster than physics allows. Instead, every large stretch of space between here and there adds to the total separation. This is why some regions of the universe may be forever beyond our reach. Light they emit now may never arrive, because the space it must cross grows too quickly. The idea can sound like a loophole, but it comes straight from modern cosmology. Expansion is not an explosion from a central point into empty surroundings. It is a change in distances throughout space itself. The strangest part is that the universe can obey its speed limit locally while still carrying distant regions away beyond light's ability to catch up. Nothing with mass can reach light speed. A rocket can keep gaining speed if it has fuel, but physics sets a final barrier it can never cross. As something with mass moves faster, its energy increases in a way that makes further acceleration harder. Near light speed, adding enormous energy produces a mere tiny increase in speed. Reaching the limit would require infinite energy, which no engine can supply. This is why particles in accelerators can get incredibly close to light speed without ever matching it. They become energetic in extreme ways, but they still remain just below the boundary. For massless particles, the situation is different. Light does not accelerate from rest like a thrown object. It exists at light speed. The rule is not a weakness of current technology. It is a statement about the structure of motion itself. The universe allows massive things to approach the limit forever, but it never lets them arrive. Light has no rest frame in ordinary physics. For almost anything else, you can imagine moving alongside it. You could match the speed of a train, a falling stone, or a drifting spacecraft. Light is different. There is no valid point of view in ordinary relativity where a beam of light sits still beside you. Every observer who measures light in a vacuum gets the same speed, no matter how they are moving. That fact is deeply strange, because it forces space and time to adjust around it. Distances and time intervals cannot remain absolute if everyone must agree on light speed. This is one of the foundations of special relativity. It means light is not just another fast thing traveling through the universe. It plays a special role in defining how events can be connected. The absence of a rest frame for light tells us that our everyday ideas of chasing, catching, and standing still break down at the deepest level. Moving clocks tick slower than stationary clocks. This effect is called time dilation, and it is not a trick caused by faulty clocks. If a clock moves very fast relative to you, you measure it ticking more slowly than a clock at rest beside you. The effect is tiny at ordinary speeds, which is why we never notice it while walking or driving. At speeds close to light speed, it becomes dramatic. Unstable particles created high in Earth's atmosphere provide a natural example. Some should decay before reaching the ground, yet many survive because their internal clocks run slower from our perspective while they rush toward Earth. Particle accelerators confirm the same rule with precise measurements. Time is not a fixed background shared by all motion. It depends on the path taken through spacetime. A fast journey does not merely cover distance. It also changes how much time passes for the traveler compared with someone who stayed behind. Fast-moving objects become shorter in their direction of travel. If a spaceship could race past you near light speed, you would measure it as shortened along its motion. Its height and width would not shrink in the same way. Only the direction of travel changes. This effect is called length contraction. The ship's crew would not feel compressed, because inside their own frame, everything aboard seems normal. The shortening appears when different observers compare measurements of space and time. It is not an optical illusion caused by poor vision. It is built into the geometry of relativity. The faster an object moves relative to an observer, the stronger the contraction becomes. At everyday speeds, the change is too small to matter. Near light speed, it becomes impossible to ignore. The idea feels absurd because solid objects seem to have fixed lengths. Physics says length is not quite so simple. It depends on motion, measurement, and the observer's frame of reference. Energy and mass are two forms of the same thing. Einstein's famous equation is often treated like a slogan, but its meaning is astonishing. Mass is not merely stuff, and energy is not merely activity. They are linked aspects of the same physical reality. A system can gain mass when energy is added to it. It can lose mass when energy leaves. This connection explains why nuclear reactions release so much power compared with chemical reactions. In a nuclear process, tiny changes in mass can become large amounts of energy. The idea also works in reverse. Enough energy can create particles with mass under the right conditions. Particle accelerators use this principle when high-energy collisions produce new particles from concentrated energy. The boundary between matter and energy is not as firm as everyday experience suggests. A solid object seems different from a beam of radiation, but physics reveals a deeper accounting system where mass and energy can be exchanged. A tiny amount of mass can release enormous energy. Nuclear reactions feel powerful because the conversion rate between mass and energy is extreme. The speed of light appears in the equation as a huge multiplier. That means even a very small mass difference can correspond to a vast energy release. In the Sun, a little mass is lost when hydrogen nuclei combine to form helium. That missing mass becomes the energy that eventually leaves as sunlight. On Earth, nuclear power plants use fission, where heavy atomic nuclei split and release energy from changes in nuclear binding. The same principle explains why nuclear weapons are so destructive, though the physics itself is not limited to weapons. It is a general rule of nature. Ordinary burning rearranges electrons around atoms. Nuclear reactions change the nucleus, where energy is stored far more densely. The ore lies in the scale. A barely noticeable amount of mass can become enough energy to power cities or illuminate worlds. Atomic clocks can measure height differences through time itself. Modern atomic clocks are so precise that they can detect tiny changes in the rate of time between two different heights. Place one clock slightly higher than another, and the higher clock ticks a little faster because it sits in a slightly weaker gravitational field. The difference is incredibly small, but the best clocks can measure it. This turns time into a tool for sensing gravity and height. Scientists can use clock comparisons to study changes in Earth's shape, underground mass, and even the movement of water. It is a remarkable reversal of ordinary thinking. We usually use rulers to measure height and clocks to measure time. Now, physics allows time itself to reveal position in a gravitational field. The effect also shows that relativity is not only about black holes or rockets. It is present between floors of a building. The pace of time changes across the world we stand on. The twin paradox is real enough to test precisely. Imagine one twin stays on Earth while the other travels through space at very high speed and returns. Relativity says the traveling twin can come back younger. This sounds like a contradiction because each twin might think the other was moving. The solution is that their journeys are not symmetrical. The traveler changes direction, accelerates, and follows a different path through space-time. Experiments with atomic clocks on airplanes and satellites have confirmed the underlying effect. Clocks that take different routes through speed and gravity do not always reunite with the same amount of elapsed time. The name paradox survives because the idea clashes so sharply with intuition. It is not a logical failure. It is a warning that time is more like a distance through space-time than a universal flow. Two people can separate, reunite, and honestly disagree about how much time passed along their own paths. Quantum physics says measurement can change what exists. In the quantum world, measurement is not always passive observation. Before measurement, a system can be described as a range of possible outcomes. After measurement, one result is found. This does not mean a human mind magically creates reality. It means that interacting with a quantum system can change the state being measured. A delicate particle can be disturbed by the very process used to learn about it. The famous uncertainty principle reflects this limit. The more precisely certain properties are known, the less precisely other paired properties can be known. Quantum measurement is one reason the microscopic world refuses to behave like a tiny version of everyday objects. You cannot always imagine a particle quietly carrying definite answers before anyone checks. Sometimes the act of checking is part of how the answer becomes definite. Nature at small scales does not simply reveal pre-written facts. It forces us to rethink what a fact is. An electron does not orbit like a tiny planet. School drawings often show electrons circling a nucleus like planets around a star. That picture is useful for a first glimpse, but it is not what modern physics says. An electron in an atom is described by a quantum state, which gives probabilities for where it might be found. These regions are called orbitals, but they are not little tracks. Some are rounded, some have lobed shapes, and some have more complex patterns. The electron does not follow a neat path that could be filmed with a tiny camera. Its behavior is wave-like, and its allowed states depend on energy and the rules of quantum mechanics. This is why atoms emit and absorb light at specific colors. The electron changes between allowed states rather than sliding smoothly through every possibility. An atom is not a miniature solar system. It is a quantum structure with patterns, probabilities, and strict energy steps. Atoms are held together by invisible electric forces. The nucleus of an atom is positively charged, while electrons carry negative charge. Opposite charges attract, and that attraction helps bind electrons to atoms. Without electric forces, ordinary matter would not have the structure we know. Every solid object, liquid drop, and living cell depends on charged particles interacting. Yet the atom does not collapse simply because electrons are attracted to the nucleus. Quantum rules determine the allowed states electrons can occupy, which gives atoms their size and stability. This balance between electric attraction and quantum structure is why matter can persist. It also explains why atoms can bond with other atoms. When electron arrangements interact, chemical bonds form and larger structures become possible. The invisible electric force reaches into every familiar object. A wooden chair, a glass of water, and the air in your lungs are all held together by charged particles following rules no eye can see directly. Chemistry works because electrons obey quantum rules. Every chemical reaction depends on what electrons are allowed to do. Atoms bond because their electrons can settle into arrangements that lower energy. They react because some arrangements are more stable than others. The periodic table is really a map of electron structure. Elements in the same column behave similarly because their outer electrons are arranged in related ways. This is why sodium reacts strongly with water, why carbon can build long chains, and why noble gases are usually reluctant to bond. The quantum rules determine which energy levels exist and how many electrons can fit into them. They also shape the geometry of molecules, which affects everything from smell to medicine. A drug works partly because its molecular shape and electron pattern interact with biological molecules in specific ways. Chemistry may look like mixing powders and liquids, but underneath it is quantum physics, deciding which structures can form and which transformations can happen. Two identical electrons cannot share the same quantum state. This rule is called the Pauli exclusion principle, and it quietly shapes the material world. If electrons could all pile into the same lowest energy state, atoms would not build the rich structures we see. Instead, electrons must occupy different allowed states. This creates the layered electron arrangements behind the periodic table. It also gives matter much of its resistance to being squeezed. When particles are forced close together, the exclusion principle prevents identical electrons from collapsing into the same state. This pressure helps support white dwarf stars, where ordinary thermal pressure is no longer enough. The rule reaches from chemistry to astrophysics. It explains why elements have distinct personalities and why certain dead stars can resist gravity for a time. A principle about identical particles becomes a reason matter has structure, diversity, and strength. Without it, the universe would be far less interesting and perhaps unable to build complex forms at all. Lasers work because light waves march in step. Ordinary light from a bulb is a jumble of many waves going in many directions. A laser is different. Its light is coherent, which means the waves are organized so their peaks and troughs line up in a controlled way. To make this happen, atoms or molecules in the laser material are energized, then encouraged to release photons that match other photons already present. The process is called stimulated emission. The result is a beam that can stay narrow over long distances and concentrate energy with great precision. This is why lasers can scan groceries, read discs, cut metal, measure distance, and guide delicate medical procedures. A laser pointer may look like a simple colored dot, but it is displaying one of the cleanest forms of organized light humans can produce. It turns a quantum effect inside atoms into a beam that can reach across a room or help probe the moon. A microwave oven heats water molecules by flipping their orientation. Microwaves are electromagnetic waves, and they interact strongly with polar molecules like water. A water molecule has an uneven charge distribution, so it tends to rotate when an electric field changes direction. Inside a microwave oven, the field oscillates rapidly, and many water molecules try to keep turning with it. Their motion transfers energy into the food as heat. The oven is not cooking from the inside out in a simple way, despite the common phrase. Microwaves penetrate some distance into food, then heat spreads by conduction. This is why a thick meal can have hot patches and cold centers. The rotating plate helps reduce uneven heating, but it does not make the process perfect. The everyday appliance is a physics demonstration hiding in the kitchen. It uses invisible electromagnetic waves to make molecules move more vigorously, and that microscopic motion becomes the warmth you feel when the food is ready. Infrared cameras see heat instead of visible light. human eyes detect only a narrow slice of the electromagnetic spectrum. Warm objects also emit infrared radiation, which our eyes cannot see. Infrared cameras translate that radiation into images we can understand. A person, a warm animal, a running engine, and a poorly insulated building can stand out because they release heat differently from their surroundings. The camera is not seeing heat as a substance. It is detecting radiation linked to temperature. This makes invisible information visible. Firefighters use thermal imaging to find people through smoke. Engineers use it to locate overheating equipment. Scientists use it to study animals at night or measure heat patterns on Earth's surface. The strange part is that darkness to our eyes is not the same as absence of light. A room can be black in visible light while glowing in infrared. With the right detector, warmth becomes a picture. X-rays pass through soft tissue more easily than bone. An X-ray image works because different materials absorb high-energy radiation differently. Soft tissues allow more X-rays to pass through. Bones absorb more because they contain denser material with heavier atoms, especially calcium. A detector captures the pattern that remains after the radiation passes through the body. The result is a shadow picture of internal structure. This changed medicine because doctors could see fractures and other hidden problems without cutting the body open. The physics is not only about penetration, it is about contrast. The beam interacts more strongly with some tissues than others, and the detector turns that difference into an image. Modern systems can refine the process further, using computed tomography to build detailed cross-sectional views. An X-ray does not show the body the way a camera sees a face. It reveals how invisible radiation is filtered by the matter it crosses. Radio waves and visible light are the same kind of thing. A radio broadcast and a beam of red light seem completely different in daily life. One carries music through the air, while the other lets you see a rose or a sunset. Physics says they are both electromagnetic waves. The difference is wavelength and frequency. Radio waves have much longer wavelengths than visible light, which is why they can bend around obstacles and travel great distances in useful ways. Visible light fits the range our eyes evolved to detect. Beyond those are microwaves, infrared, ultraviolet, X-rays, and gamma rays. They all belong to the same family. This makes the electromagnetic spectrum one of the most unifying ideas in physics. A foam signal, a rainbow, a heat lamp, and a hospital scan are not separate kinds of magic. They are variations of one phenomenon. Change the wavelength, and the same basic thing can become communication, color, warmth, or imaging. Color is your brain interpreting different light wavelengths. There is no red object sending redness into your mind as a little package. An object absorbs some wavelengths of light and reflects others. Cells in your eyes respond to parts of the visible spectrum. Then your brain builds the experience we call color. This is why color depends on lighting, vision, and context. A white shirt can look different under sunlight and under a strange indoor bulb because the light falling on it has changed. Some animals see ultraviolet patterns that humans miss completely. Some people have forms of color blindness because their cone cells respond differently. Color is real as an experience, but it is not a simple property sitting alone inside objects. It is a relationship between light, matter, eyes, and brain. Physics begins the story with wavelength. Biology finishes it by turning those signals into the vivid world we think we are simply seeing. A mirror reverses depth, not left and right. It feels as if a mirror swaps left and right, but that is not quite what happens. A mirror reverses the direction perpendicular to its surface. The front-back direction is flipped. Your face appears behind the glass because light rays bounce in a way that creates a virtual image at an equal distance beyond the mirror. Left and right may seem switched because you imagine turning yourself around to match the reflection. If you raise your right hand, the hand on the same side of the mirror image rises. The confusion comes from comparing your body to a person facing you. The mirror itself does not know left from right. It follows a simple reflection rule about angles. This familiar bathroom object is quietly teaching geometry. Every glance shows that our brains add interpretation to what light actually does. The mirror is not lying. It is revealing how reflection and perception meet. Polarized sunglasses block light vibrating in one direction. Like waves can vibrate in different orientations. When sunlight reflects from a flat surface like water, road, or snow, much of the reflected glare becomes polarized in a particular direction. Polarized sunglasses contain filters that block that dominant orientation. The result is reduced glare and clearer vision. This is why they are useful for driving, fishing, and bright outdoor conditions. The effect can be demonstrated by looking at certain screens or by rotating one polarizing filter in front of another. At one angle, much light passes through. Turn it far enough, and the view can darken dramatically. The glasses are not simply making everything dimmer. They are selecting which light vibrations reach your eyes. That makes them a practical example of wave physics you can wear on your face. A pair of sunglasses can reveal that light has orientation, not just brightness and color. Soap bubbles reveal light interference in shimmering colors. A soap bubble is surrounded by a very thin film. Light reflects from the outer surface and also from the inner surface. Those reflected waves meet each other. Depending on the film's thickness, some colors are strengthened while others are cancelled. As the film drains and changes shape, the colors shift. That is why a bubble can ripple with blues, greens, pinks, and golds before it pops. The colors are not painted onto the soap. They are created by interference between light waves traveling along slightly different paths. The same principle appears in other thin films, but bubbles make it delicate and visible. Their beauty is a measurement of thickness, but the scale of light's wavelength. A child watching a bubble float is seeing wave physics in motion. The surface is fragile, but the rule behind the shimmer is exact. Tiny changes in thickness decide which colors survive. Oil-slick colors come from waves cancelling and reinforcing. When a thin layer of oil spreads across water, light reflects from both the top and bottom of the oil film. Those reflections overlap. Some wavelengths line up and become brighter. Others fall out of step and fade. The result is the shifting rainbow pattern often seen in a puddle after rain. The colors depend on the thickness of the oil film, which can vary from place to place. That is why the pattern looks uneven and alive. It is not the same as a normal pigment color. It comes from interference, where light waves combine differently depending on path length. This effect also helps scientists and engineers study very thin coatings. A messy street puddle can show the same physics used in precision optics. The surprising lesson is that color can come from structure rather than dye. Sometimes what you see is not a material's color, but a wave pattern made visible. Noise-canceling headphones use sound to erase sound. Sound waves can add together, but they can also cancel each other. Noise-canceling headphones use microphones to listen to outside noise, then electronics create a matching sound wave with opposite pressure changes. When the unwanted wave and the generated wave meet, they reduce each other. This works especially well for steady low sounds like engine rumble. Sudden, sharp sounds are harder because the system has less time to respond. The headphones do not create silence by blocking every vibration physically. They use interference turning sound against itself. It is a wonderfully direct example of wave physics becoming everyday technology. A cabin full of drone can feel calmer because tiny speakers are producing carefully timed pressure changes near your ears. The idea sounds almost impossible at first. You add more sound, and the result can be less sound. Physics allows destruction to happen through perfect coordination rather than brute force. A violin string vibrates in many patterns at once. When a violinist draws a bow across a string, the string does not produce only one simple vibration. It supports a fundamental vibration and many higher patterns called harmonics. These extra vibrations help create the instrument's tone. The wooden body of the violin then responds, amplifies, and colors the sound before it reaches the listener. Change the finger position, and the vibrating length of the string changes. That changes the pitch. Change bow pressure or speed, and the mix of harmonics changes too. This is why the same note can sound different in different hands. The physics is not cold or mechanical in the dull sense. It is the reason expression is possible. A single stretched string becomes a rich sound because it can vibrate in layered ways at the same time. Music turns wave behavior into emotion, but underneath the beauty is a precise conversation between motion, resonance, and material. Resonance can make bridges sway dangerously under repeated pushes. A small push can have a large effect if it arrives at the right rhythm. That is resonance. Every structure has natural ways it prefers to vibrate. If repeated forces match those patterns, the motion can grow. A child on a swing shows the safe version. Each well-timed push adds energy, and the swing rises higher. Bridges, buildings, and machines can respond in similar ways under wind, footsteps, or rotating equipment. Engineers must account for this when designing large structures. They try to avoid dangerous matching between outside forces and natural frequencies. Sometimes they add dampers, which absorb energy and reduce motion. Resonance is powerful because it does not require a single huge shove. It can build from many smaller inputs arriving in step. The lesson is both simple and unsettling. Timing can matter as much as strength. Under the wrong rhythm, a stable structure can begin to move. But Tacoma Narrows Bridge showed wind can feed vibration. In 1940, a suspension bridge in Washington state began twisting dramatically in strong wind and then collapsed. The event was filmed, and the footage became one of the most famous engineering lessons ever recorded. The bridge did not fail merely because the wind was strong. Its design allowed wind to feed energy into twisting motion. As the deck moved, airflow around it changed in a way that reinforced the motion further. The result grew until the structure could not survive. This disaster helped change how engineers think about aerodynamics in bridges. A bridge must not only hold weight, it must behave safely in moving air. The Tacoma Narrows collapse is often simplified as resonance, but the real story involves aeroelastic effects, where structure and airflow interact. That makes it even more fascinating. A solid bridge became part of a dynamic system, and the wind found a way to keep adding energy. A whip cracks because its tip breaks the sound barrier. A whip does not make its sharp crack simply because lever slaps the air. When the handle is moved correctly, a wave travels down the whip toward the tip. As the whip narrows, the moving energy is carried by less and less material, so the tip accelerates dramatically. It can exceed the speed of sound in air. The crack is a tiny sonic boom. This means a simple hand tool can produce supersonic motion without an engine. The physics depends on the whip's taper, flexibility, and timing. The wave must travel smoothly enough for energy to concentrate near the end. That concentration turns an arm motion into a fast-moving tip with startling speed. It is an example of how shape can transform motion. The sound is brief, but the mechanism is remarkable. Long before aircraft broke the sound barrier, humans had already done it with a flick of lever. Sonic booms happen when pressure waves pile together. A moving object usually sends pressure disturbances ahead through the air. At ordinary speeds, those disturbances spread away before the object arrives. Near the speed of sound, the object begins to catch up with its own waves. Once it passes that speed, the waves cannot move ahead fast enough to warm the air. They stack into a shock wave that trails behind the object in a cone shape. When that cone crosses your location, you hear the boom. It is not a single noise made only at the moment the aircraft breaks the sound barrier. It can follow the aircraft along its path, reaching different listeners at different times. This is why supersonic flight over populated areas is carefully controlled. The boom is the sound of air being compressed very suddenly. A jet does not merely move through the atmosphere. At high enough speed, it forces the atmosphere to rearrange itself violently. Airplanes fly because wings redirect air downward. A wing is not simply held up by air sliding faster over the top. That idea is only part of a larger story. A flying aircraft supports its weight by pushing air downward. The air pushes back upward on the wing, and that upward force is lift. Wing shape, angle, speed, and airflow all matter. Tilt the wing slightly into the oncoming air, and it changes the direction of the flow. The pressure around the wing adjusts as the air speeds up, slows down, and bends. This creates a force large enough to hold a heavy machine in the sky. The engines do not lift the plane directly. They provide forward motion, which lets the wings keep working. Flight feels impossible because metal seems too heavy for air to support. Physics makes it practical by turning motion through air into a controlled exchange of momentum. A plane flies by, giving the air a downward shove. A curveball swerves because spinning air changes pressure. When a pitcher throws a spinning baseball, the ball drags nearby air around with it. On one side, the spin works with the oncoming airflow. On the other side, it works against it. This imbalance changes the pressure around the ball and creates a sideways force. The result is the curve that can fool a batter even when they know it is coming. The ball is not changing direction because it has a hidden engine. It is being pushed by the air it disturbs. The same effect helps explain why spinning footballs, tennis balls, and golf balls behave differently from non-spinning ones. Skill in sport often means learning to control invisible fluid motion. A pitcher's fingers create rotation. Rotation changes airflow, and airflow nudges the ball across its path. What looks like athletic magic is a moving physics lesson, delivered too fast for the eye to fully unpack. Boiling water cools because energetic molecules escape first. At the surface of hot water, some molecules are moving faster than others. The fastest ones have enough energy to break away into vapor. When they escape, they carry energy with them, leaving the remaining liquid with a lower average energy. That is cooling through evaporation. It is the same reason sweat helps cool your skin. The water molecules that leave your body take heat away as they enter the air. Boiling intensifies this process because bubbles of vapor form within the liquid and rise out. The key is that temperature is an average, not a promise that every molecule has the same energy. A pot of water contains a crowd of particles with different speeds. The quickest are the first to leave. That makes boiling more than a bubbling spectacle. It is a sorting process where the most energetic molecules escape and the liquid they leave behind can cool. Steam burns badly because it releases hidden heat. Steam at boiling temperature can injure skin more severely than liquid water at the same temperature. The reason is phase change. When water becomes steam, it absorbs a large amount of energy without changing temperature. That stored energy is called latent heat. When steam touches cooler skin, it condenses back into liquid water and releases that energy directly onto the tissue. Then the newly formed hot water can continue transferring heat. This double effect makes steam especially dangerous. The strange part is that a thermometer may show the same temperature for boiling water and steam, yet the steam can deliver far more energy during condensation. Physics reminds us that temperature is not the whole story. Heat depends on how much energy is transferred and how matter changes form. A cloud from a kettle may look soft and harmless, but it can carry a concentrated thermal surprise. A pressure cooker raises water's boiling temperature. In an open pot, water boils when its vapor pressure matches the pressure of the air above it. A pressure cooker traps steam, which increases the pressure inside the sealed vessel. Under higher pressure, water must become hotter before it can boil. That hotter water cooks food faster because heat moves into ingredients more aggressively. Beans soften sooner, tough meat breaks down more efficiently, and grains cook with less waiting. The cooker is not using a mysterious cooking force. It is changing the boiling point by changing the surrounding pressure. The sealed environment also keeps more moisture inside, which helps transfer heat through steam and liquid together. This is everyday thermodynamics with a locking lid. The hiss of a pressure valve is not just a kitchen sound. It is a safety system managing stored energy. By controlling pressure, a simple pot changes the temperature range that water can reach. Metals feel colder because they carry heat away faster. Touch a metal spoon and a wooden table in the same room. The metal usually feels colder, even though both objects may be at the same temperature. Your skin is not measuring temperature directly. It is sensing how quickly heat leaves your body. Metal conducts heat well, so it pulls energy from your skin rapidly. Wood conducts poorly, so heat leaves more slowly, and it feels warmer. This is why a tile floor can feel cold on bare feet, while a rug beside it feels comfortable, even in the same room. The sensation is about heat flow, not just the object's temperature. The same idea explains why metal tools can feel painfully cold in winter. They drain warmth from your fingers fast enough for your nerves to react sharply. Physics turns a simple touch into a measurement of energy transfer. Coldness is often the speed of losing heat. Fire is glowing gas and particles releasing energy. A flame is not a solid object, even though it has a shape you can point to. It is a region where chemical reactions are happening fast enough to produce heat and light. Fuel molecules break apart and combine with oxygen, forming new substances while releasing energy. That energy heats nearby gas and tiny particles until they glow. The blue part of a flame often marks more complete combustion. The yellow glow can come from hot soot particles radiating light before they burn away. A flame keeps its shape because hot gases rise and fresh oxygen flows in. Remove heat, fuel, or oxygen, and the reaction stops. Fire feels ancient and familiar, but it is a dynamic process rather than a thing. It is matter changing partners at high speed, with released energy becoming warmth, motion, and light. A candle flame is chemistry made visible through physics. Fluorescent materials absorb invisible light and release visible light. Some materials can take in light at one wavelength and emit light at a longer wavelength. Under ultraviolet light, they may glow in colors that seem to appear from nowhere. The incoming light gives electrons in the material extra energy. When those electrons drop back down, they release some of that energy as visible light. The emitted light has lower energy than the absorbed light, which is why invisible ultraviolet can become a bright, visible glow. This effect appears in highlighter ink, security markings, minerals, and biological imaging. It is also used in lamps and scientific tools. Fluorescence is not the same as reflection. A fluorescent object is not merely bouncing light back. It is absorbing energy, briefly storing it in electronic states, and sending part of it out again in a new form. The glow is a tiny energy conversion event repeated by countless molecules. Some materials remember their shape after being bent. Shape memory materials can return to a previous form when heated or triggered in another way. The most famous examples include certain metal alloys, such as nickel titanium. Bend a wire made from one of these alloys, then warm it, and it can spring back to a programmed shape. The effect comes from changes in the material's internal crystal structure. At lower temperatures, one structure can be deformed more easily. When heated, the atoms shift into another arrangement that restores the original form. This is not memory like a brain stores a picture. It is memory built into atomic geometry. These materials are used in medical devices, eyeglass frames, actuators, and clever mechanical systems. The fascination is that a solid object can appear to remember what it used to be. Heat unlocks a hidden instruction written into the way its atoms prefer to arrange themselves. Non-Newtonian fluids can harden suddenly under impact. Some fluids refuse to behave like ordinary liquids. A sheer, thickening fluid can flow when handled slowly, then stiffen when hit or squeezed quickly. The particles inside it are suspended in liquid, and under sudden stress they jam together. The material becomes temporarily harder because the particles cannot move past one another easily. When the stress is removed, it can loosen again. This makes the behavior feel almost alive, even though it is just physics. Researchers study these materials for protective gear, flexible armor, and impact-absorbing systems. The appeal is obvious. A material that stays soft during normal motion but stiffens during a blow sounds almost like science fiction. The key is that its response depends on how force is applied over time. Ordinary liquids have predictable flow. Non-Newtonian fluids make motion itself part of the answer. Push gently and they yield. Strike quickly and they resist. Cornstarch and water can act solid when punched. Mix cornstarch with water and you get a strange substance, often called oblak. Move your fingers through it slowly, and it flows like a thick liquid. Punch it or slap it, and it can feel solid for an instant. The grains of starch are packed in water, and sudden force can make them jam together. The water cannot move out of the way fast enough, so the particles lock into a temporary structure. This is why people can run across a pool of the mixture if they keep moving fast, but sink if they stop. It is a perfect hands-on physics experiment because the effect is immediate. You do not need special equipment to feel the rule. The material responds to the speed of your motion. A bowl of kitchen ingredients becomes a lesson in how matter can switch behavior when stress arrives too quickly. Granular materials can flow like liquids and jam like solids. Sand, rice, gravel, and grain are made of separate pieces, yet they can pour through a funnel like a fluid. They can also lock together and support weight like a solid. That dual nature makes granular materials surprisingly complex. A pile of sand forms a slope at a particular angle because grains slide until friction and gravity reach a balance. Shake the pile, and it can settle into a denser arrangement. Force grains through a narrow opening, and they can suddenly jam. This matters in industries that move powders and in natural events like landslides and avalanches. It also explains why a bag of rice can feel soft one moment and rigid the next if the grains press tightly together. Granular physics sits between simple categories. These materials are not liquids, but they can flow. They are not solid blocks, but they can carry loads. Their behavior comes from contact, friction, and crowding. Sand dunes sing when grains slide together just right. In certain deserts, a sliding dune can produce a deep humming sound that carries across the landscape. The effect happens only under special conditions. The sand grains must have the right size, shape, dryness, and surface coating. When a layer of grains avalanches down the dune, many grains move in a synchronized way. Their collisions create vibrations that the dune can amplify. The result can sound like a low musical note or distant engine. Not all dunes do this, and even a singing dune may stay silent when the sand is damp or disturbed. The phenomenon shows that a landscape can behave like an enormous natural instrument. The sound is not coming from wind alone. It is produced by countless grains moving together with unexpected order. A dune may look still for days, then suddenly reveal that its surface can turn motion into a voice. Static electricity can make your hair repel itself, rub a balloon on hair, and electrons can move from one surface to another. This gives the hairs the same type of electric charge. Like charges repel, so the strands push away from each other and stand outward. The effect looks playful, but it reveals a basic rule of electricity. Matter may usually seem neutral, yet tiny charge imbalances can create visible forces. Dry air makes static effects stronger because charge has fewer easy paths to leak away. That is why sparks are more common in winter or in low humidity. When you touch a metal doorknob after walking across carpet, stored charge can suddenly move, creating a small shock. Static electricity is electricity out of balance. It can lift hair, cling clothes together, and make dust stick to surfaces. The forces are small, but they are direct evidence that invisible charge can push and pull ordinary objects. A balloon sticks to a wall by shifting electric charges. After a balloon is rubbed on fabric or hair, it can gain extra electric charge. Bring it near a neutral wall, and the charges inside the wall respond. Opposite charges shift slightly closer to the balloon, while like charges shift slightly farther away. The wall as a whole remains neutral, but the near side becomes more attracted than the far side is repelled. That tiny imbalance can hold the balloon in place. Nothing sticky has been added. The balloon is clinging through electrostatic attraction. This effect is called polarization, and it happens because charges in matter can rearrange a little under an electric influence. The same general idea helps explain why small bits of paper jump toward a charged comb. It also shows why neutrality is not the same as being unaffected. Even an object with no net charge can respond strongly when charges inside it are nudged into a new pattern. Lightning begins with charge separation inside storm clouds. Inside a storm, rising and falling air throws ice crystals, droplets, and soft hail into constant collisions. Those collisions help separate electric charge within the cloud. One region becomes more negatively charged, while another becomes more positive. The exact details are complex, but the result is a growing electric field. The air normally resists electrical flow, yet a strong enough field can break that resistance. At that point, the atmosphere becomes a path for a sudden discharge. The ground beneath the storm also responds, because charges there shift under the influence of the cloud. What looks like one bright flash begins as a huge hidden imbalance built by turbulent weather. A thunderstorm is therefore not only a rain machine. It is a charge sorting system with moving ice, violent air currents, and enormous stored electrical energy. Lightning is the moment that imbalance finds a way to release itself. Earth itself acts like a giant magnet. Our planet has a magnetic field that reaches far into space. It is not produced by a bar magnet hidden inside Earth. The field comes from motion in the planet's outer core, where electrically conducting liquid metal moves under the influence of heat, rotation, and convection. This moving metal generates electric currents, and those currents produce magnetism. The field is not perfectly steady. It shifts, wanders, weakens, strengthens, and has reversed direction many times in Earth's history. Its presence matters because it helps guide charged particles from space and shapes a protective region around the planet. Without it, the upper atmosphere would be more exposed to the solar wind. The magnetic field is invisible, yet it is one of Earth's great active systems. Beneath our feet, deep metal motion helps create a shield that extends far above our heads. The ground is part of a planet-sized electromagnetic engine. Compasses work because molten metal moves beneath Earth's crust. A compass needle aligns with Earth's magnetic field, which is why it can point roughly north. That field is generated deep below the crust, not at the surface. In the outer core, liquid iron-rich material moves as Earth loses heat from its interior. Because the material conducts electricity, its motion helps sustain the geodynamo. The compass needle responds to the magnetic field produced by that deep process. It does not point exactly to the geographic North Pole. It points toward magnetic north, which drifts over time. Navigators have long had to account for that difference. The simple needle in a compass is therefore connected to a churning layer thousands of kilometers below. Holding one in your hand links you to Earth's interior. A small pivoting magnet becomes a surface instrument for a hidden planetary machine, one that has guided travelers across oceans, deserts, and skies. Auroras happen when solar particles strike Earth's atmosphere. The sun releases streams of charged particles into space. When those particles reach Earth, many are guided by the planet's magnetic field toward polar regions. There, they collide with atoms and molecules high in the atmosphere. Those atmospheric particles gain energy, then release it as light. Oxygen can glow green or red, while nitrogen can produce purple, blue, or pink tones. The colors depend on altitude, particle type, and energy. An aurora is not simply sunlight reflecting from the sky. It is the atmosphere being excited by space weather. During strong solar storms, auroras can spread farther from the poles and become more intense. They are beautiful, but they also signal activity that can affect satellites, power systems, and radio communication. The shimmering curtains overhead are a visible connection between Earth and the Sun. They show that our planet sits inside a changing flow of charged matter. Plasma is the most common ordinary matter in the universe. On Earth, solids, liquids, and gases feel like the main states of matter because they fill our daily experience. Across the universe, plasma dominates. A plasma is a gas-like state in which electrons are separated from atoms, creating a mixture of charged particles. Because it contains charges, plasma responds strongly to electric and magnetic fields. Stars are made of plasma. The glowing material in nebulae can be plasma. Lightning and auroras involve plasma too. Neon signs and plasma globes use smaller, human-made examples. The reason plasma is so common in space is that high temperatures and energetic radiation can strip electrons away from atoms. Once matter becomes charged, it behaves in ways an ordinary gas does not. It can flow along magnetic fields, form filaments, and produce light. Plasma reminds us that the familiar states of matter are local comforts. The wider universe is often charged, glowing, and magnetically shaped. The sun is made mostly of plasma, not fire. Fire needs chemical fuel and oxygen, but the sun is not burning in that ordinary sense. Its visible surface and deeper layers are made mostly of ionized gas. Electrons and nuclei move through a hot, charged state of matter. The sun glows because energy from its interior heats this plasma until it emits intense radiation. Its surface boils with huge convection cells, while magnetic fields twist through the charged material and help produce sunspots, flares, and loops of glowing gas. Thinking of the sun as fire makes it seem like a giant campfire in space. The real object is far stranger. It is a self-gravitating sphere of plasma held together by gravity and powered from within. Its behavior depends on nuclear physics, fluid motion, radiation, and magnetism. Every sunrise is the light of a star whose surface is not flame, but a vast ocean of charged matter. Fusion powers stars by joining light atomic nuclei. In a star's core, gravity creates enormous pressure and temperature. Under those conditions, light nuclei can get close enough for the strong nuclear force to bind them together. In stars like the Sun, hydrogen nuclei ultimately form helium through a chain of reactions. The final helium nucleus has slightly less mass than the starting ingredients. The missing mass becomes energy, which slowly works outward and eventually escapes as light. Fusion is difficult because positively charged nuclei repel each other. A star succeeds by crushing matter into conditions that make rare close encounters happen constantly across a huge volume. This is why stars can shine steadily for immense spans of time. They are not using ordinary fuel. They are converting the simplest atoms into heavier ones, while releasing energy from the deep binding of nuclei. Fusion is the engine that makes starlight possible and turns gravity into a cosmic power plant. Fission splits heavy atoms and releases stored nuclear energy. Some heavy atomic nuclei are unstable enough that splitting them can release energy. In fission, a nucleus such as uranium can absorb a neutron, become disturbed, and break into smaller nuclei. Additional neutrons may fly out, and those neutrons can trigger more fissions. This chain reaction can be controlled in a reactor or released rapidly in a weapon. The energy comes from the way nuclear binding changes when a heavy nucleus becomes smaller, more tightly bound pieces. It is not chemical burning. Electrons around the atom are not the main actors. The nucleus itself is being rearranged. Nuclear reactors use this process to heat water, produce steam, and drive turbines that generate electricity. The astonishing part is the density of energy. A small amount of nuclear fuel can release vastly more energy than the same mass of ordinary chemical fuel. Fission shows how much power can be stored inside atomic nuclei. Radioactive decay is random for each individual atom. A radioactive atom has no tiny clock hand showing exactly when it will decay. For one atom, the moment of decay is unpredictable. For a large collection of identical atoms, the pattern becomes reliable. Half-life describes how long it takes on average for half the atoms in a sample to decay. This combination of randomness and predictability is deeply quantum. It means scientists cannot say when a specific unstable nucleus will change, but they can forecast the behavior of enormous numbers with remarkable accuracy. The process can release particles or radiation as the nucleus moves toward a more stable state. Radioactive decay powers some natural heat inside planets and provides tools for medicine, industry, and archaeology. Its strangeness lies in the scale shift. One atom behaves like a row of the dice. A large sample behaves like a clock. Nature can be fundamentally uncertain and statistically precise at the same time. Carbon dating works because unstable atoms decay at predictable rates. Living things take in carbon while they are alive, including a small amount of radioactive carbon. After death, exchange with the environment mostly stops, and that radioactive carbon begins to decay without being replaced. By measuring how much remains, scientists can estimate when the organism died. The method is especially useful for once-living materials such as wood, cloth, bone, and charcoal within a certain age range. It does not date rocks directly in the same way because it depends on biological carbon intake. The power of the technique comes from half-life predictability. Individual atoms decay randomly, but the average behavior of a large sample is stable enough to become a time-measuring tool. Carbon dating turns nuclear physics into a way of reading history. A fragment of ancient wood can carry a fading atomic signal, and that signal can help reveal when a fire burned or a tree was cut. Particle accelerators recreate conditions from the early universe. In a particle accelerator, electric fields give particles enormous energy, and magnets steer them around carefully controlled paths. When particles collide, their energy can concentrate into a tiny region for an instant. That can produce new particles and interactions similar to those that existed when the universe was much hotter and denser. These machines do not recreate the whole early universe like a miniature explosion. They recreate specific high-energy conditions on a microscopic scale. Detectors surrounding the collision points record the debris, allowing scientists to reconstruct what happened. The results help test the deepest models of matter and forces. Accelerators have also led to practical technologies in medicine, materials research, and imaging. The fascination is that humans can build a machine on Earth that briefly touches regimes of nature otherwise found only in cosmic extremes. A collision lasting less than a blink can reveal rules written into the earliest moments of reality. The Higgs field gives many particles their mass. The Higgs field is thought to fill all of space. Some elementary particles interact with it strongly, and those interactions give them mass. Others interact weakly or not at all. The Higgs boson is a particle associated with this field, and its discovery confirmed a major piece of the Standard Model. The idea is often simplified, but its importance is enormous. Without the Higgs mechanism, many particles would not have the masses needed for atoms and ordinary matter to exist as they do. The field is not a material fog slowing particles down in the usual sense. It is a quantum field with a non-zero value even in empty space. Particles behave differently because of how they relate to it. This makes mass feel less like an obvious built-in property and more like a relationship with something everywhere. The weight of matter has roots in a field we do not directly see. Antimatter exists, and it annihilates with ordinary matter. For many particles, physics allows a matching antiparticle with the same mass and opposite charge. The electron has the positron. The proton has the antiproton. When matter and antimatter meet, they can annihilate, converting their mass into energy and other particles. Antimatter is not fiction. It is produced naturally in some radioactive decays and cosmic ray interactions. It is also created in laboratories and used in medical imaging through positron emission tomography. The mystery is why the visible universe contained so much matter and so little antimatter. The early universe should have produced both in great abundance, yet something caused matter to win by a tiny margin. That small imbalance allowed stars, planets, and people to exist. Antimatter shows how symmetrical the laws of physics can be, then points to one of the biggest unsolved questions. Why is there something made of matter here, instead of equal matter and antimatter vanishing into radiation? Physics can explain both galaxies and a falling raindrop. The same subject reaches from the largest structures we can observe to the smallest events in daily life. It describes how galaxies gather under gravity and how a drop of rain forms, falls, flattens, and breaks apart in air. That range is what makes physics so powerful. It does not treat the universe as separate compartments of wonder. It searches for rules that connect motion, energy, matter, light, and force across every scale. A raindrop is shaped by surface tension, airflow, gravity, and collisions with other droplets. A galaxy is shaped by gravity, motion, dark matter, gas, and time. The details are different, but the ambition is the same. Physics asks what the world is doing and why it behaves that way. It can make the ordinary feel larger and the cosmic feel more understandable. Look closely enough, and even the smallest event becomes an entrance into the machinery of reality. And so we have reached the end of tonight's journey through the strange, surprising world of physics. We have moved from empty space that is not truly empty to clocks that change their rhythm under gravity. We have followed light as it bends, splits, stretches, and carries messages across the universe. We have looked inside atoms, where solid things become mostly space, and where invisible forces hold the familiar world together. We have drifted past moons, planets, stars, black holes, and galaxies. We have seen how the sun spends its own mass to shine, how gold may begin in the collision of dead stars, and how the largest structures in the cosmos can be shaped by forces too subtle to feel in your hand. And we have returned to ordinary things too. A mirror, a bubble, a flame, a violin string, a raindrop, and a balloon on a wall. Each one carries a small piece of the same deep story. Physics is not only out there in space. It is here, in the room, in the air, in warmth, color, motion, and sound. If you enjoyed this journey, you are very welcome to like the video, subscribe, or leave a thought below. It helps more people find this little corner of science and sleep. And if you happen to still be awake, there is another video waiting on the screen for you now. But for now, let the facts begin to fade into the background. Let the strange machinery of the universe keep turning without needing your attention. Let your shoulders soften, your breathing slow, and your thoughts become lighter. You do not need to hold on to any of it. The stars can keep shining. The atoms can keep moving. The night can take care of the rest. Sleep well, and good night.